Okay, everyone, welcome to reInvent. My name is Ian. This is my colleague Hunter, and we're here to talk to you today about how to simplify building your applications with AWS SDKs. Let's go ahead and get started. So to give you a little bit of background about the AWS SDKs, SDKs cover more than 350 different AWS services, including a few new ones that just launched this week at reInvent. Across those 350 services, there are more than 14,000 different operations or API calls that one can make. And the AWS SDKs have to support each of those. Further, the SDKs are available in 12 different programming languages, and we're always looking at adding more to meet the needs of our customers. And then finally, the SDKs are released on a daily cadence. That means that when a new feature or new service is announced, within 24 hours, it should be available to use in one of our SDKs. Across our SDKs, we support a number of key features, like authentication to secure your data in the cloud and make sure that no one accesses or tampers with your resources. Profile files, which capture configuration for interacting with AWS that ranges from very simple to very complex. Automatic retries, so that when transient problems happen on the internet or there are occasional hiccups with contacting an AWS service, your data stays resilient and your operation can continue as expected. Waiters, paginators, endpoint resolution, and a whole bunch of other things that we're going to talk about in this presentation. So how do we enable all this? How do we provide all of these features in all of these languages for all of these services? The answer is that we've learned to take somewhat of a holistic approach to the developer experience. We start by thinking about what the customer is trying to achieve in their application, and then look backwards to how they can build that using AWS tools and AWS services. We build on the lessons that we've learned from the past, both the things that work really well that we should do more of, and the things that haven't gone so well that we should do less of. We're working on driving consistency into the SDKs so that what works one way in, say, the Java SDK works the exact same way in Python and Rust and Swift. And then lastly, we're focused on prioritizing simplifications to the SDK. When we notice that customers are interacting with our services in a particular way over and over again, we look for ways to build that behavior into our SDKs to reduce the complexity of interacting with AWS. So what we're going to cover today are three main topics. The first of which is ModelDriven API Development and how we use that at Amazon to build the best possible APIs, and how you can adopt the principles of it in your own applications. We're going to look at how the SDKs are more than just HTTP clients, more than just thin wrappers around calls to a web service, but they actually have several pieces of client-side logic and constructs enabled. And then lastly, we're going to talk about the pluggable architecture of the SDKs, how they're being re-architected to make them more extensible, more customizable, to meet the challenges of the next set of services and the next set of features that we're going to roll out. With that, I'm going to hand it off to Hunter.
All right, thank you, Ian. So I'm going to be talking about model-driven API development, what it is, how we use it at AWS to scale with the number of services we have and the number of languages we support, and also how you can use this approach in your applications. Before I do that, I want to go back in time about 20 years to when everyone was still texting with physical keyboards and AWS was just getting started. Back then, we had only a few services, and these services supported only a few simple operations. For example, S3 supported a simple put operation that allowed you to put an object into a bucket, and you could then get that same object back. Back in this world, it would have been fairly straightforward for us to handwrite our SDKs. But over time, as we added new features for customers and supported new use cases, the number of services we had grew from just a few to now over 350, and you've probably seen a few new services launched at reInvent this year. At the same time, the number of languages that we support has increased. We now support 12 different programming languages, and we're always looking to add new ones. In addition to supporting new services, we also have to support new features for existing services in our SDKs. In the past year alone, we added over 3,000 new features from services into our SDKs. We also release these SDKs daily. We have to synchronize these releases to make sure that a developer at reInvent who wants to program in, let's say, Python, doesn't get a feature at a different time than a developer that wants to program in maybe Rust. Now, how do we deal with all of this? We have over 350 services, we support 12 different languages, and we have thousands of features we need to incorporate into our SDKs every year. As you might have guessed, the answer is model-driven API development. Okay, so what is model-driven API development? Well, as the name suggests, it means that we start from a model. This is a contract between the client and the server that defines the interface that we provide to our customers. It's typically defined in a purpose-built interface definition language, or IDL. This IDL can be used to generate both client-side and server-side code, and can also incorporate additional metadata that would be hard to represent in typical programming constructs. For example, you might want to include, for a given operation, a set of example inputs and outputs that need to be generated into the API documentation. We can represent these in this IDL. One of the additional advantages, beyond just being able to generate code in multiple different languages for many different services, is that model-driven API development also starts from the customer experience, the interface that customers actually interact with, and works backwards from there. Now, AWS has used a model-driven approach from the early days. There have been a number of different iterations of internal modeling languages. And from deploying these languages, or from using these modeling languages in actually deployed production services, we've learned a lot about how to do model-driven API development right, and we've also learned a lot about how not to do model-driven API development. The end result of all of this hard-won learning is Smithy. Now, Smithy is an open source, protocol-agnostic interface design language. It can be used to generate server-side and client-side code in many different languages, and it forms the core of all of AWS's modern SDKs, including JavaScript, Rust, Kotlin, and Go. Now, there are over 90 AWS services that have been built with Smithy from the ground up. And in addition to all of those public services, there are also thousands of internal models. To give you an example of what a Smithy model might look like, we have on the side here a simple weather service. This service allows you to get the forecast for a given city. It also allows you to get the current time. Now, I want to point out a few things with this example. The first of which is that Smithy encourages a resource-based approach to API design. The second thing that I want to note is the REST JSON1 trait. Now, I noted earlier that Smithy is protocol agnostic. What this means is that the interface definition language does not tie you to any specific wire format. It does not require that you use JSON or some binary protocol or XML. Instead, we allow users and service teams to define the protocols that they need to use for their services. All right, let's walk through an example of what it might look like to take an operation and code generate it into some of our different SDKs. The example we have here is a create queue operation. This is very similar to what you might find in Amazon SQS. It takes in some input, returns some output, and might throw a number of errors. Now, one of the great things about Smithy and model-driven API design is that the service teams implementing this don't need to worry about the implementation details of these in each of the different SDKs. Instead, we can use Smithy code generation to create idiomatic SDK code in all of our different languages. So on the side here, we have some examples in Kotlin, TypeScript, and Go of what this operation might look like when it's actually generated into an SDK. Now, we talked a bit about what model-driven API development is. I want to give you some insight into how we use it at AWS to actually build SDKs. As the name suggests, we always start from a model. Now, we typically edit this model in just a standard IDE. Now, Smithy supports linting as a first-class concept. What this means is that you can encode additional checks on your models, such as enforcing some kind of naming standard. Now, once you've addressed any linting concerns and gotten a syntactically correct Smithy model, teams at AWS are just going to commit that to version control as they would any other code. Their teams are then going to review this to make sure it's consistent with their existing models. We want to provide a consistent experience for a service. And they're also going to make sure it conforms to the expected interface. Once they've done that, and teams are ready to actually publish this code to an SDK, they can publish it to an internal platform tool. Our internal platform tool performs additional consistency checks to make sure that we're following AWS best practices, but it also uses a built-in tool of Smithy called Smithy Diff. What this tool does is it allows us to ensure that we're not shipping any backwards incompatible changes into our SDKs. We never want to break existing customers with new features. So once we've passed the consistency checks and backwards compatibility checks, our teams are then assigned an additional API reviewer who does a final check to make sure that our APIs are meeting our quality bar. Once that API reviewer has approved their changes, our teams are then going to create preview builds. This allows them to build the SDKs as they would actually be presented to customers and allows them to test these changes locally to ensure that we're, once again, providing the best customer experience we can. Once our teams are happy with those changes that they've tested locally, they can then schedule them for publishing. On the day that we've scheduled these changes for publishing, we're going to use code generation to generate the changes into all of our different SDKs and to generate our API reference documentation. Now, one of the best parts about model-driven API development is we're able to make all of this, up until code generation, self-service for service teams. This allows teams at AWS to focus on delivering features for their customers and allows the SDK teams to focus on generating the highest quality, most idiomatic code they can for each of the languages we support. Now, I told you a bit about how we use model-driven API development at AWS. I'm going to walk through an example really quick of how you might use it in your applications. So let's say, for example, you have a service gateway. And this gateway will proxy requests to multiple different backend services. And you want to maintain a consistent model for this service gateway. That can get quite complicated if you have a number of backend services, and also additionally extra complicated if you also want to support a large number of different SDKs. So what can we do? We can define Smithy models for service A and service B, which are example services that we might proxy these requests to. And we can then combine these two models together to create our gateway model. Now, we can use these service models to actually code gen service stubs. Now, let's say, for example, that service A is a queuing service for a gaming system, and that service B is a leaderboard for the same gaming system. They may have some common types, for example, a user. One of the nice things with Smithy is we're able to pull that common model out into a separate Smithy package so that we can reduce duplication across our different models. Now, we've gotten this common gateway model. We can now use Smithy and the Smithy toolchain to generate an open API spec that we could maybe upload to define an API gateway endpoint. We can generate documentation. And we can also use Smithy in order to generate SDKs for this service gateway. OK, so how does all of this simplify building applications for you? Well, one of the key things is that model-driven API development allows AWS to scale the number of to scale our SDKs with the number of services we have, and also to support additional SDK languages. Model-driven API development also allows us to deliver features for customers faster, without losing focus of the customer experience. And then finally, Smithy is an open source project, so you can use it today in your projects. All right, I'm going to hand it back to Ian.
Thanks, Hunter. So Hunter just took us through how the API-driven, or how the model-driven API design process gets new APIs into our SDKs. Now we're going to dive a little bit into the SDKs themselves and what features they add on top of those APIs to make life a little bit easier. Let's start with an example of asynchronous service operations. Some services that you call may return a result very quickly. For instance, a user calling Amazon's DynamoDB with the create table operation will receive a response back almost immediately, indicating whether the operation will succeed or will fail. But behind the scenes, the table is not created when the response is sent. The table is created asynchronously because it takes some time to set up things like replication, availability in multiple zones, proper access via roles and security, bandwidth concerns, and other things. So rather than make the user wait for all of that to happen before sending the response back and holding an HTTP connection open for that long, the service responds asynchronously and continues its work in the background. This can get into trouble, though, if users then immediately turn around and issue a subsequent call to that same service that depends on the previous operation having completed. For instance, if the user tries to use the put item API to insert a row into that DynamoDB table, they may get a response back that indicates an error. No such table exists. So knowing that this is a possibility and that this is a pattern that some services use, many of you will have written code that looks somewhat like this. There's a lot going on in this example, but there's two functions, and the top one detects whether a table has been created or not. It does so by issuing a described table API call to DynamoDB, looking at the status that comes back in the response and checking to see if it's active. If it's active, then we can return true, this table does exist. If, on the other hand, we catch an error, and that error's name is something like resource not found exception, then that means that the table doesn't yet exist, and we should return false from this method. Finally, if we catch any other kind of error, it means that something has happened that we don't quite fully expect, and the table creation is unlikely to succeed. So we should probably just throw the error anyway and deal with it at some other point in our business logic. Below this function is another function called poll table creation. This one calls isTableCreated in a loop until it finally receives a true response, indicating that the table does exist. As long as we're receiving false, we're awaiting approximately 3 seconds between each of those calls so that we're not just hammering the service with useless traffic that's likely to return the same thing. This kind of client-side abstraction is called a waiter. Previously, there was no good way to model waiters alongside of our other APIs. The logical backup to do then would have been to write waiters by hand in our SDKs. But unfortunately, as you've seen, as the scale of AWS grows in terms of number of services and number of operations which are asynchronous, there just became far too many to write by hand. The SDK teams simply don't have enough resources or enough time to write all of these individual waiters from scratch. So what that left us with, unfortunately, was that you all had to write the waiters yourselves. When you needed one, you had to write code similar to what was on the previous slide. And that led, unfortunately, to code bloat in your applications, difficult to detect bugs, odd race conditions, basically nothing good. Now, waiters are modeled as a first-class feature in Smithy. This Smithy model shows an example of the waitable trait applied to the described table operation. The trait called table, or the waiter called table exists, has a couple of different states that it can be in. A success state where the table status is active, and a retry state where the error that's received is resource not found exception. Anything that doesn't match one of these two states is considered an error condition and would get thrown back to the caller to deal with through their regular business logic. As with everything else in Smithy, this gets code generated into our SDKs so that clients can use them with a minimal amount of boilerplate. Here's examples in TypeScript, Kotlin, and Swift of invoking the waiter that was the same waiter we saw on the previous slide. You can see that we've shrunk the amount of code necessary in your application from 20 plus lines down to just 4 or 5. And those 4 or 5 lines are much simpler to read and to reason about what's happening than that larger block of text. Let's move on to another example of paginated service operations. Some service API calls return not just one item worth of data, but a whole list of data. And whenever you're returning a list of data, it's a wise idea to truncate that list at some point so that your clients don't have to deal with arbitrarily large responses. That can cause out-of-memory issues, resource saturation, and even denial of service attacks. So an example of a paginated service operation is DynamoDB's query API. DynamoDB will return back a maximum of 1 megabyte of items, and then it will stop. The way that a user knows that they have gotten a truncated result set is that alongside those items, there will be a token. The token will indicate that that's where the service stopped processing the results and where a future call to the API could resume processing the results. That token then has to be passed by the user into a subsequent query call, which itself may return another set of truncated results, which may contain yet another token indicating that another call is necessary. In this manner, we chain the token from prior responses into subsequent requests until we finally receive back a response that contains no token. That indicates that no truncation occurred, we've reached the end of our result set, and no more API calls are required to get that logical result set. All right, so knowing that this is a possibility with some APIs, some of you will have written code that looks like this. This code sets up a call to the query API in DynamoDB. It also sets up a variable for tracking what's called the last evaluated key, or the token that we were talking about on the prior slide. Then, inside of a loop, it invokes the query API call, passing that key if there is one. It interprets the response, and it does some business logic to handle each item, which isn't shown here. But then the final thing that loop has to do is take the key that was returned in the response and potentially pass it into the next request that will happen on the next iteration of the loop. And this loop will continue until that last evaluated key winds up being null or empty. This type of client-side abstraction is called a paginator. Just like waiters, paginators are now modeled in Smithy. You can see here an example of the query operation annotated with the paginated trait. The paginated trait indicates where the token gets input into an API request and where the token comes out in an API response. It also contains some other fields for doing things like, for instance, limiting the number of results that are returned in a single page. This paginator is then code-generated into our SDKs, and you can see examples here of using the paginator in both Rust and Kotlin. And again, compared to the prior slide, this is far less code necessary in your applications in order to get the same benefit. Let's look at one more example, event streams. Event streams are bisynchronous or bidirectional asynchronous transfers of data between a client and a service. A client is streaming data to a service, and simultaneously, in parallel, the service is streaming data back to the client. These kinds of operations happen over protocols that support bidirectional transfer, like HTTP2. There's a number of interesting use cases for where these could be beneficial, and one of them is audio transcription. So let's say that a user has a fairly large audio file that contains speech, and they want to feed that into some system and get out a text transcript so that they can use that in some other way in their application. Event streams allow the user to stream that audio file to Amazon Transcribe, and for Amazon Transcribe to begin streaming the results back simultaneously. The SDK takes care of chunking that audio file into pieces, sending the individual requests, and then also interpreting the individual responses from the server and assembling those into an asynchronous data flow object that can be consumed by the user. In this way, users aren't required to keep an entire audio file all in memory all at once, for example, nor are they required to keep the entire text transcript in memory all at once. They can stream from disk, they can stream back to disk or to other parts of their application, and all of this happens through mechanisms provided by the SDKs. Let's take a look at one final feature. Let's take a look at one final feature in our SDKs, and that are smart defaults. So what we found over decades of developing web services and developing clients for them is that not every application in any given environment requires the same defaults and configuration as another application in a different environment. What we've discovered is that there are several different default modes that can be used to automatically configure sensible defaults for interacting with AWS services that can then be further customized by users as they see fit. These modes are a standard mode, which is kind of a generic catch-all for undifferentiated applications. Another mode is the in-region mode, where your application exists within a single AWS region and doesn't make calls outside of that region to access other resources or other services. There's a cross-region default mode where your application, again, is based in one region, but does make calls across the world to access resources in another region, say calling from the US to Europe. And then finally, there's a default mode for mobile applications. Mobile applications somehow have some of the most challenging network conditions given spotty network connectivity, network congestion, and even losing connectivity when you move out of the coverage range of a given mobile carrier. All of these different default modes optimize various settings within the SDK, such as retry behavior, timeouts, and regional endpoints. So to give you an example, in the in-region default mode, the timeouts are configured to be very narrow and very strict. That's because if you're making calls from a region to other things in that same region, you expect the network latency to be very low, you expect responses to be very fast. And if they're not, you want to fail quickly so that you can either retry them soon, or you can give up and have some upstream process retry them for you. But if you're in a mobile application, you want much longer timeouts. You want to give a lot of time for that network congestion to work out, for maybe a connection drop and reconnect to happen. And so the connections wind up, or the timeouts wind up being much longer. All right, so how do all of these features simplify building applications? Well, for starters, they make a common set of patterns available across all of the SDKs, no matter what language you're using, no matter what services you're developing with, no matter what environment you're running in. And importantly, what works one way in one service or one environment or one language is transferable knowledge. It will work the same way in another language with another service in another environment. The code is written by AWS and tested by AWS, so that's work that you don't have to do, and surety that you can have that someone else has put the thought in and the work in to make sure that this works the way it's expected to. All of this combines to let you write less boilerplate, less mostly useless code focused on interacting with AWS SDKs, and more time focusing on your own business logic, the thing that provides value to you and to your customers. With that, I'll hand it back to Hunter.
All right. Thank you, Ian. Okay, so I'm going to be talking a bit about the internals of the SDKs, how they work under the hood, as well as giving you some insight into where the SDKs are headed. Now, everything Ian's just been talking about happens at the API layer of the SDKs, right? So basically how you interact with the SDKs. Maybe you provide the SDKs with some input, the SDKs handle actually going and calling a service, and they provide you back some output. However, there's a lot that happens inside the SDKs to actually get you that output from your input. So let's dive into that a little deeper. Now, all of our SDKs need to go through what we call the request pipeline. This is the standard set of steps they must perform in order to take your input and deliver you an output. The first step is to serialize your request into the correct wire format. So maybe we need to serialize your request into an HTTP request that has some JSON body. However, before we can even do that, we have to go and determine what the correct wire format for a given service is. In order to do that, we have to go through a process that we call endpoint resolution. What we go and do is we determine for a given service in a given region what endpoint to use. That tells us what wire format to use as well. So once we've determined the correct wire format, we can then start the process of serializing your shape. While we're doing that, we check that all the inputs that you've provided conform to any constraints that the services have put on these inputs. Maybe there's an integer that needs to be between some minimum and maximum value. Maybe there's some string that must conform to some pattern. So once we've verified your input and serialized it to the right wire format, we then need to sign it. Signing is important because this is how the service that you're calling actually verifies that you are who you say you are and that you're allowed to do what you're asking to do. Once again, before we can even go and create a signature, we need to go and determine the auth scheme. This tells us both how to attach the signature to your request, but it also tells us what signature algorithm to use. This can vary, once again, from different services and different regions. So once we determine the correct algorithm to use and how to attach the signature to your request, we still have one more thing to do. We have to go and get your credentials. This can happen a number of different ways depending on your environment. It happens differently if you're in an EC2 instance. It happens differently if you're on an ECS container. It happens differently if you're on a local box. You can also provide your own custom credentials provider to the SDKs. However the credentials are provided, the SDKs need to go and use the credentials provider to actually get your credentials, and we can then take that, use the correct algorithm to generate your signature and attach it to the request in the correct way. Once we've done that, we're ready to call the service. Or not quite. We still have to go and actually get a connection. One of the issues with connections is you can actually starve your system of connections. The SDKs handle this for you by managing a connection pool and connection queue, and they will actually go and get a connection for you to the service and use that connection to make the call and receive a response. Once you receive a response, we need to deserialize it into some kind of actual programming object that you can use. But before we can do that, we need to determine what type to deserialize it into. If you're using an event stream, you may have multiple different types that are possible in the response. Once we've determined the correct type, we then also need to check any checksums that might have come along with your response. Some of our services include additional checksums that allow you to verify the integrity of the data you've received. So once we've checked these checksums, we've determined the correct type, we're ready to deserialize your response. Well, sometimes requests on the internet fail. Maybe a packet got dropped, maybe a cosmic ray caused a bit flip, or maybe a mole chewed through a cable. Whatever the reason, we need to be able to retry requests. The SDKs handle this for you by first determining if a request is retriable. And if it is, then the SDKs will use a token bucket and exponential backoff approach in order to make that retry. This is important because you can unintentionally cause a retry storm if you don't have the correct retry strategy. What a retry storm is where a service is temporarily down, and when it's down, all the clients start retrying requests. When the service comes back up, it can then get saturated by the clients all retrying at once. The SDKs take this token bucket and exponential retry approach in order to mitigate the chance of that happening. Now, over time, all of our SDKs have evolved to implement this request pipeline in slightly different ways. And what that means is we've occasionally ended up with divergent and occasionally conflicting approaches in different languages. So how do we harmonize all of our different SDKs across all of our different languages so we have a consistent customer experience? Well, the answer is the Smithy reference architecture. The Smithy reference architecture is a common architecture for all of our SDKs that emphasizes modularity, observability, and extensibility. What do we mean by modularity? Well, all of the common behaviors of that request pipeline, in the Smithy reference architecture, we've taken all of those and we've defined them as clearly delineated modules. We call these runtime components. Each of our different services can use some subset of the runtime components. For example, S3 needs to use all of the runtime components in order to perform all the operations it does. However, some of our clients, such as S3 Glacier, don't need some of this functionality. For example, S3 Glacier does not use event streams. Now, what this means is with the Smithy runtime architecture, we can start to vend clients that only include the modules that they need, minimizing the runtime overhead of all of our clients, keeping the size as small as possible so that your applications run as fast as possible. However, that's not the only benefit of this modular architecture. Each of these runtime components are individually configurable. And you can also even swap out runtime components for custom implementations. What this means is both AWS services and you, the customers, can implement custom behavior. For example, an AWS service might customize the way in which we perform endpoint resolution, or you, the user, might customize the way in which you want your SDKs to perform retries by providing your own custom implementation of these modules. Now, there's one other benefit of this modular architecture. Each of these common runtime components can be used by you, the customer, to actually build your own SDKs. Now, Smithy reference architecture isn't just about modularity. All of our SDKs already emit all three of the major telemetry signals: metrics, logs, and traces. However, in the past, the way in which they've emitted these signals has been inconsistent, and the format of these signals has not been standardized. The Smithy reference architecture standardizes the types and format of these signals so that you can be confident that you have the same signals across all your different SDKs and that they're easily parsable. The Smithy reference architecture also standardizes the mechanism by which you can forward these signals to an existing observability backend. For example, AWS X-Ray, Amazon CloudWatch, or OpenTelemetry. This allows you to get insights into how the SDKs are performing in your applications. All right, let's return back to the request pipeline for a minute. Before and after each stage of the request pipeline, you might want to read or modify that request. The Smithy reference architecture standardizes the integration points for the request pipeline. For example, you could modify a request before signing, you could read a request after transmitting it, or you might read a request after deserializing it. These standardized integration points can be plugged into using a mechanism we call interceptors. Let's walk through a simple example of an interceptor. Let's say that you're running the AWS SDKs, but you want to send requests through a proxy. This proxy is going to take those requests and forward them to AWS. However, this proxy requires an additional header. Because this additional header is getting stripped off by the proxy, you don't want to include it in the signature. So how can we do this? Well, what we can do is we can use interceptors to plug into a standardized integration point to modify the request and add the header we need. On the screen, you'll see an example of interceptors implemented in both Rust and Kotlin. And in both of these cases, we implement an interceptor that plugs into the modify before transmit integration point, gets the request, gets the headers for that request, modifies them, and then forwards that request on to the next stage of the request pipeline. Now, these interceptors can be registered either for every request from a client or just for a specific operation. Here on the screen, you'll see an example of those interceptors we just defined in the last slide being added to every request for a client in both Rust and in Kotlin. Now, the purpose of the Smithy reference architecture is to harmonize the implementations of our SDKs. However, there's still more work to be done. The good news is that all of our new SDKs, including the recently announced Rust and Kotlin SDKs, and the Swift SDK, which is in developer preview, already support the Smithy reference architecture. The SDK teams are also working to incrementally add support for the Smithy reference architecture to all of our existing SDKs. Finally, we plan to open source the Smithy reference architecture. This will provide you with reference documentation that defines how all of the runtime components are defined and how they interact with one another and how you can create custom implementations. It also will define all of the common integration points that we discussed earlier and give you examples of how you can plug into them with interceptors. And then finally, this reference documentation can be used as a roadmap to implement your own SDKs using Smithy code generation and our runtime components. So how does all of this simplify building applications for you? Well, first, it gives you a set of common integration points that you can use to customize the behavior of requests in our SDKs. Secondly, it gives you a common set of signals that you can forward to your existing observability backends in order to get insight into how the SDKs are behaving in your applications today. The modular architecture, defined by the Smithy reference architecture, also allows us to minimize the runtime overhead of our clients so that your applications can run faster and be smaller. And then finally, the customizability of this modular architecture allows both AWS service teams and customers to implement new capabilities with the SDKs that they never could have before without involvement from the SDK teams. All right, I'm going to hand it back to Ian.
Thanks, Hunter. So we've talked a little bit now about model-driven API development, how it's used at Amazon, and how it can be used in your own applications. We've talked about the features that the SDKs provide that make them more than just simple HTTP clients. And Hunter's just taken us through the pluggable architecture that SDKs are being built on to enable customizability and extensibility. What all of these features combine to provide are a common set of features in multiple languages, for multiple services, in multiple environments. All service clients support some or all of these features where applicable. We offer simplified integration between your application and AWS SDKs, such as through interceptors, which can be used to customize requests and responses, and observability, where you can send metrics and trace and logging data to observability backends to measure how your SDKs are performing. Finally, all of this allows you to spend more time focusing on your own business logic and less time focusing on the SDKs themselves. For more information about some of the things we've talked about today, visit these QR codes for AWS developer tools and for Smithy itself. We have great documentation and even places where you can submit requests and features that you'd like to see added to these developer tools and to Smithy. One last thing I'll say is please make sure to fill out the survey in your mobile app on this session.